There we go. All right, let's put this up out of the way. Yep. Okay. So by now, you should have memorized all the symbols that I asked you to do. Okay. And we're going to use that as our alphabet and form compounds. But central to all formation of compounds where you combine two or more elements together, we need an understanding of the bonding process. And we've essentially, over the years, divided bonding into two types: ionic bonding and covalent bonding. And both are an expression of attractive forces that hold atoms together in a compound. And these compounds can be as small as, I don't know, laughing gas, nitrous oxide, or they can be as complicated as, let's see, what's a good example? Well, I can't draw it because it's too big, but starch is a good one. That's a pretty huge molecule. Lots of proteins are big molecules. They're combinations of different elements, and they fall under a special category called polymers. But they can vary in size. They can be very small, they can be huge. And they can be a combination of bonding models, either ionic bonding or covalent bonding. Now, as so often happens, let's see, we got another zoomer. Okay. As so often happens in the sciences, we educate lots of scientists, and they go off and they do their little projects, their pet projects for years and years and years, and they develop all this information. But most scientists don't put it together into a coherent story. They just tell enough of the story so they can get a publication and boost their resumes. But occasionally, once in a blue moon, they might say, a mind comes along that takes all that information and synthesizes it into a coherent story. You might even call it a theory. One of those persons was Linus Pauling, who received the Nobel Prize in chemistry in 1954 for a previous work he had done. In fact, he published a book called The Nature of the Chemical Bond. And based on that and some other of his work, he was awarded this prize. That was back when Nobel Prizes actually meant something. Not when you can get a Nobel Prize for being the first Black president. Okay, so let's focus on the ionic bond at this time. For an ionic bond to occur, we need a difference in charge. I mean, a complete difference in charge, positive, negative. And to do that, ions have to be transferred from one atom to the other. And when they do that, for instance, we have sodium here, chlorine here, and the sodium atom will transfer one of its electrons to chlorine. So that leaves sodium deficient in one electron, which gives it a positive charge. Right? We can't mess with the protons, but if you take a negative away, that leaves an excess of positives. Now sodium has a positive charge. And now chlorine's got an extra negative, which gives it a negative charge. And the only thing holding them together now is electrostatic attraction, positives and negatives. They form a bond. Now that's just one atom of sodium and one atom of chlorine. What actually happens is billions of these atoms go through this dance, and they end up in a crystal structure where you have sodium positives and negatives in a matrix. And you can see, you can get an idea of what that matrix looks like on the microscopic level if you look at the solid crystal under a microscope or a magnifying glass. Just spill some salt on the table and get a magnifying glass and look at it. What do you see? Never looked at it before? You see little tiny cubes, perfect cubes. That's because this positive is surrounded by fluoride negatives, and then they're surrounded by positives. So you get this crystal matrix. And there's front and back too. So this sodium has 6 chlorides around it. This chloride has 6 sodiums around it. And they form this matrix. And the nature of the ionic bond, the physical structure of the crystal is displayed in the macroscopic world by a cube. But the key to ionic bonding is purely electrostatic attraction. When you transfer one or more electrons from one atom to the other, you throw them out of balance, electrically speaking, because you can't change the protons. If you add an electron, you get a negative. If you take away an electron, you get a positive. So that's the basis of the ionic bond, is that electrostatic attraction. The covalent bond, on the other hand, oh, by the way, the ionic bond always occurs between a metal and a non-metal. So you know where those are located on the periodic table. You just need to remember where that, well, on this table, it's a red line. That stair-step line defines non-metals on the right of it, metals on the left of it. For the covalent bond, you know, this works fine for metals and non-metals. We can understand electrostatic attraction, but we have compounds that are made up of 2 non-metals. Okay, how do you explain that one? Because we've learned over the decades that metals have a tendency to lose electrons in chemical reactions, and non-metals have a tendency to attract electrons. So this one makes sense. The metal loses electron because it wants to, and the non-metal because it wants to. But what do you do when you have a non-metal and a non-metal, right? They're both fighting over the electrons. Well, we had to come up with another form, and that was, by the way, this is an ionic compound. I want to stick with the terminology that's used in your textbook. And these are covalent compounds. So what we had to do is come up with another model. And the non-metal and non-metal for a covalent compound share electrons. Think of it as, I sure would like to have a bicycle. But my brother wanted a bicycle too. My parents couldn't afford 2 bicycles. So we had to share the bicycle. And sometimes we both rode on the same bicycle. When we did that, we were a covalent compound. We shared the bicycle. In this case, they share electrons between the 2. Your example here was sodium chloride, metal, non-metal. Over here, a good example is water. Right? You have an oxygen and 2 hydrogens. And the electrons are between them, and they're sharing them. Now, I've always got to give you flies in the ointment. The fly in the ointment here is that most bonds are not purely ionic or purely covalent. They usually share some character of either one. Some of them are very covalent with just a little bit of ionic character. Some of them are extremely ionic with practically no covalent character. But there's this continuum in between them where the ionic character and the covalent characters kind of overlap. Okay. Now, these electrons that are being transferred or shared are not all of the electrons that are available in the atom, right? So sodium has 11 electrons, right? 11 protons, 11 electrons until it loses one. Now it has 10 electrons, right? Chlorine has 17 when it's neutral. Now it has 18 electrons, right? So that one has 18, this one has 10. And that accounts for the difference in charge. But especially for covalent bonding, the electrons that participate in the bonding process are not all of the electrons. In other words, we can divide the electrons as a non-participating or participating. And the non-participating are called core electrons. And that's just what they are. They're closest to the nucleus. The ones that are transferred or shared are in the outer regions. Those are available, and they're called valence electrons. Valence electrons. Those are the ones we're interested in when we talk about bonding. And there are various methods that have been devised over the years for simplifying the description of valence electrons so that we can sort of get a handle on what to expect when we get two atoms together. How are they going to behave? One of those rules is the octet rule. Right? Have you had anatomy and physiology or a biology class? They might have mentioned the octet rule. For many of the elements in the periodic table, they're happiest when they can claim 8 electrons in their valence shell. Now, that's not true for all of them. It's true mostly for the second and the third period, right? The one starting with lithium and the one starting with sodium. Those, all the way across, those elements tend to fit pretty well with the octet rule. When you get down into the fourth, well, potassium and calcium behave pretty well. Some of the other elements on the right-hand side do okay. But when you get into the transition elements, then the octet kind of falls apart, right? Because we learned that which orbitals do they have access to? They have access to d orbitals, right? And d orbitals can have 10 electrons, whereas the 2 columns on the left are filling s orbitals, and the 6 on the right are filling p orbitals. So 2 plus 6 equals 8. When you've got just the s and the p's involved, that lends itself to an octet. We'll talk more about that later. I just introduced the topic here. So ionic bond has to transfer electrons from one atom to another. The valence electron, we sort of mentioned it here, but by definition, the valence electron is an electron in the outermost shell of the atom. And it is one that is active in forming a bond. Now we can even narrow it down further. and say these valence electrons in our octet model are found in either the S or the P subshells in the representative elements or the noble gases. Now, I mentioned the representative elements, which ones those were. When they say representative elements, if you read that, it's going to be either elements in the first two columns on the left or the last six on the right. Those are the representative elements. I don't know why they call it that. Represent what? Represent octets? I don't know. Maybe it's just grandfathered in. Okay. So these are valence electrons. They're the ones that participate in the bonding process. Now, there was a scientist several years ago. I think he was American. His name was G.N. Lewis. He was interested in finding a simple way of representing elements and their valence electrons so that he could visualize how they reacted with one another. And he came up with this Lewis, now we call it the Lewis dot structure. Have we done that yet? I don't think we have. Okay, good. Because I don't want to hammer it if it's already been beat down already. So what he did was, his model was based upon the octet. So you just write the symbol, right, like sodium, and you say, okay, how many electrons are available for bonding? How many valence electrons are available to sodium? Well, if you look at where sodium's located in that first column, that means there's only one electron in the s orbital. For sodium, it would be the 3s orbital, right? So that 3s has one electron, and that one is available for bonding. So you just put one dot there. That's it. That's all sodium has available to it for bonding. If you go on the other side to chlorine, chlorine has, if you remember from last chapter, chapter 3, I think, when we were drawing the electronic structures, the highest orbitals for chlorine are the same, similar for sodium, and we have 3s, but it's got 2 electrons in it. And then we have 3p, and it has 5 electrons in it. Right? And then you have the 1s and the 2s, 2p over here. But these are the ones that are valence. So we have 7 electrons that are valence electrons. So we position those around this symbol. And the best way to do it so that you don't violate any of previous rules that we came up with, it just started one at a time. 1, 2, 3, 4, 5, 6, 7. There we go. So we have 7 dots for 7 electrons, and these are only the valence electrons. Okay. So we have 7 around chlorine, 1 around sodium. That's a Lewis symbol, and here's some other symbols, and they're based upon the same reasoning. Right? If we go next door to sodium, we have magnesium right here, and it has 2 electrons in the s orbital. Right? That's it. That's the valence electrons. So magnesium would only have 2 dots, and you don't pair them up until you start filling. It's Hund's rule. So you go around individually, and then you can start pairing them up after you've gone around one time, and you have 2, 4, 6, 8 maximum. So there's your octet possibilities. So everybody in the second column has 2 electrons, valence electrons available. And then you go to the far side of the representative elements, you find aluminum has 3, silicon has 4, phosphorus has 5 dots, sulfur has 6, and chlorine has 7. And notice if you keep going, you get to the noble gases. Notice the noble gases are full. All the noble gases, except for helium, noble gases have 8 electrons in their valence shell. Helium and hydrogen are different because they only have access to the 1s orbital. So technically speaking, hydrogen and helium follow the duet rule. If you got 2 electrons for hydrogen or helium, then you're full. All right. So let me see. Are we gonna? I don't want to steal my own thunder. Let me get my hard copy here. Just a second. Okay, yeah, I'm going to get to it in a minute. So I'm not going to jump my own gun. Okay, and you can do that for any element. You can do that Lewis dot structure. In fact, we can do Lewis dot structures for compounds too, but that's later. All right, so let's see if we can do Lewis dot structures for these. Calcium. Where's calcium on the periodic table? That one's about gone. Let's get another one. There we go. So see where calcium is? It's in the second column. That means it has 2 electrons. So we have here 1 and 2. That's the Lewis dot structure for calcium. How about selenium? Where's selenium? It's right under sulfur. Right? So we're in the 4th period, and we've got 2 from potassium and calcium, and then gallium is 3, germanium is 4, arsenic is 5, and selenium is 6. So we have 1, 2, 3, 4, 5, 6. And that's the same Lewis dot structure that you will have for anyone in that family. Sulfur would be the same, oxygen would be the same. Has 6 valence electrons. Carbon. Where's carbon? Well, carbon's in the 2nd period. So you go lithium, beryllium, boron, carbon. That's 4. 4 electrons for carbon. Okay. There we go. The explanation. Now we're going to do something with this, right? It's not just busy work. Okay, we got some generalizations we want to go through just to put the last nail in the coffin. Representative elements in the same group have the same number of valence electrons. I just made that point with oxygen and its group, the chalcogens. 2, the number of valence electrons for representative elements is the same as the Roman numeral periodic table group number, or count from left to right, skipping the transition elements. Okay. When you created that extra credit for the periodic table, I had you name it the new way, 1 through 18. But the old way has Roman numerals. So if you notice up there, this table still has them. The first group is 1A, second group is 2A. You go over to boron, is 3A, carbon's 4A, nitrogen's 5A, so forth and so on. And that Roman numeral is the number of valence electrons. So if you have that on a table, then you don't have to count. But if you don't have it, just count from the left to right, skipping the transition elements. So if we say we go from rubidium in period 5, rubidium, strontium, indium, tin, antimony, tellurium, and iodine. Still got 7, just like all the members of the halogens. The maximum number of valence electrons for an element is 8, based upon the octet rule. So once you've got 8 electrons around that symbol, it's full. How about these? We should be able to do these fairly quick. Oxygen, it's in count 6 over. Right? 1, 2, 3, 4, 5, 6. There's oxygen. Phosphorus. Phosphorus is 5 over from the left. So it's 1, 2, 3, 4, 5. Fluorine. It's just like chlorine. right? It's in the halogens, so it's going to have 2, 4, 6, 7. All right. Here we go. There we go. And there we go. All right. A valence electron is an electron in the outermost electron shell of an atom. Shorthand method developed by a scientist to represent the number of valence electrons is Lewis symbols, or electron dot symbols. I've always heard it called Lewis dot structure, but that's more. Lewis dot structure implies compounds. And there's the octet rule. These arrangements of valence electrons are ideal when forming a compound if you can get 8 electrons available to the element. That's where they're most stable, because they think they look like noble gases. That's what everybody is tending toward, noble gases. Everybody wants to be the Joneses with a Mercedes or a Beamer, you know, something like that. Okay, so they try to form a noble gas configuration, whether it's ionic bonding or covalent bonding. Now, ionic bonding is pretty straightforward, right? You transfer the electron over and then you count around that element symbol. But for covalent bonding, we have to sort of stretch the rule a little bit. All right, there's the octet rule. Definition first. If we're going to form an ion, this is just a reminder. A loss of electrons will give you a positive ion. A gain of electrons will give you a negative ion. The negative ions are called anions. And the positive ions are called cations. So this would be an cation, and this would be an anion. Examples. And just a reminder, in big letters, don't mess with the protons. All right. I don't know if this helps or not. It's just sort of a pretty picture. What happens to a neutral atom of sodium when it loses an electron? Well, the picture is relatively accurate. When you lose an electron, you gain a positive charge because you have one extra proton. But you also shrink the size. The size of the atom depends on the electrons too. Because the nucleus is so small, most of the size of the atom is due to the electrons. So if you take an electron away, it shrinks. And for chlorine, if you add an electron, it balloons out. Okay. Give the chemical symbol for each of the following ions. The ion formed when a potassium atom loses 1 electron. Remember, if it loses 1 electron, it's neutral to start with. Loses an electron, now it's 1 positive. Let's see. There it is. How about sulfur when it gains 2 electrons? Okay. Now, while we're here, sulfur is in the oxygen group, so it's going to have 6. It's going to be 6 like this. 1, 2, 3, 4, 5, 6. So if it gains 2 electrons, it's got an octet. And now it has a 2- charge. That's when elements are happiest, when they can fill those valence shells. Okay, atoms can either lose or gain electrons, resulting in the formation of ions, which are either cations or anions. Okay. This is what we're trying to do here with this example, is to show that the tendency to lose or gain electrons. Oh, wonderful.
No, meeting, I didn't want to mention.
That's worth interrupting. Now we won't be locked out of the lab. So the illustration here is for sodium, right? Let's do it without looking at that. Sodium has 11 protons, 11 electrons in its neutral state. So it's going to have 1s2, 2s2, 2p6, that's 10, and then a 3s1. Okay. Now, if we're going to have an octet somewhere in this electronic structure, is it easier to go to add 1 plus 6 or 7 to make that a 2 and this is a 6? It'd be kind of difficult to do, to add that many electrons with only 11 protons. So what does sodium do? It loses that electron. Now it has an octet, right? If it loses an electron, now it has an octet in the second orbital rather than in the third. So the way to look at it on the periodic table is, say sodium's there. What if we back up 1? Right? We lose that electron, so we back up to where does this occur? Right? If we go backwards from sodium by losing an electron, we get to neon with 10 electrons, right? 2, 4, 6 is 10. So in this case, this sodium ion has the same electronic configuration as neon. Yeah. So it has a noble gas configuration. Right? It's much more difficult to add enough electrons to make a noble gas configuration when you've only got 1 to lose. The energies involved are just, it would destabilize. Right? You would destabilize the atom because all those negatives in there, without the positives to hold them down, are going to be pushing on each other. So it's not going to happen. The elements, the metals, that's why the metals tend to lose electrons and work their way backwards to a noble gas configuration. Whereas the nonmetals are closer to the noble gas configuration by simply adding electrons. All right. So what we have is a generalization, so that if we look at the first column there of elements, the alkali metals, that's why they always tend to form 1 positive charge ions when they form ionic compounds. So lithium +1, sodium +1, potassium +1, rubidium +1, cesium +1. That's always the case. The next door neighbors, beryllium, magnesium, calcium, strontium, barium, they tend to lose 2 electrons because they have 2 electrons in their s orbitals. And if you lose 2 electrons, you back up 2 places, now you're at a noble gas configuration. And at the 3A group, which is boron doesn't quite fit that because it's a non-metal, but aluminum, gallium, indium, those guys tend to be a 3+ charge because it's easier to lose 3 electrons and go backwards than it is to gain 5 electrons and go forwards. And remember those charges also, because when we start naming compounds, the fact that you know those metals are fixed charge will help you in understanding the naming rules. Nonmetals, on the other hand, tend to gain electrons. So if fluorine gains 1 electron, it's going to look like neon, electronically speaking, right? It's got an octet now. Oxygen, though, it has to gain 2 electrons to look like a noble gas. And nitrogen would have to gain 3 to look like a noble gas. Now remember, when we say they're losing and gaining electrons here, we're talking about ionic compounds. We're not talking about covalence yet. We're still ionic. So if we had something like, I don't know, sodium nitride. We haven't given you naming rules yet, but that's what it's called. This would be a 3-, this would be a 1+, so we'd need 3 of them. So Na3N would be that compound, because each sodium lost an electron and this nitrogen gained 3 electrons, so that they're all happy. They all look like noble gases now. You can think of that as the driving force for ionic compound formation, is the gain or loss of electrons to give noble gas configuration. The carbon group is kind of wonky. They're in the middle. They're halfway in between. So depending on the compound, it could go either way. They could gain 4 electrons or lose 4 electrons. And actually, that's not so bad because of the way carbon behaves. We can form, oh my, thousands and thousands and thousands of new compounds with carbon as the basis. That's why organic chemistry is a massive branch of chemistry, because you can do so much with it. Okay, this is just a way of visualizing the electronic configurations of various elements. If they have exactly the same electronic configuration, they're known as an isoelectronic series, or they're isoelectronic species. In our example here, a 3- nitrogen and a 2- oxygen and a 1- fluorine all have the same electronic configuration. 1s2, 2s2, 2p6. Sodium loses an electron, magnesium loses 2 electrons, aluminum loses 3 electrons. They all have the same electronic configuration too. And that electronic configuration looks like neon for all of these. We could stick neon in there and it would be isoelectronic with all of those ions. Okay. I don't think we need to hammer this one anymore. Let's see. Is this in the way? Is it? It's covering up a little bit there. Choose an alkaline metal, an alkaline earth metal, a noble gas, and a halogen, so that they constitute an isoelectronic series when the metals and halogen are written as their most stable ions. Okay, instead of doing neon, why don't we do argon? Right. Argon would be 18, and it would have the configuration 1s2, 2s2, 2p6, 3s2, 3p6. Let's see, that's 8, that's 10, 8, 18. That's it. So anybody else that would have that configuration is isoelectronic. Well, if we go to the right and say potassium, potassium has 19 electrons. So we'd have to lose one of those electrons to look like this, because it would have a 4s1. So we get rid of that one. Now we look like argon. Or we go the other direction, chlorine. Chlorine has 17. So it would be 1 less here. It would be 3p5. Add an electron. Now you got the same configuration. Okay. Okay. I didn't go to calcium. Potassium. Yeah, did potassium. I didn't go to calcium. Calcium would just have to lose 2 electrons to get that configuration. And there it is. The number of electrons for each species is 18. The number of protons is different for each one. Remember, if you mess with the protons, you change the element. So the number of electrons will be the same, but the number of protons will be different because they're different elements. Right? Okay. What's the electronic configuration of magnesium ion? Let's see, magnesium is in the second column, alkaline earths. So it's going to have a 2+ charge when we get done with it. Right? Magnesium has, what is it? 12. So we could say 1s2, 2s2, 2p6, 3s, that's 10, 2. So if we get rid of those, now we have a 2+ charge. Okay. And that would be, there it is. Okay. So when we form an ionic compound, all we need is that for the metals to give up electrons and the non-metals to accept the electrons, and then we have an electrostatic attraction. Positives and negatives attract each other. And the force of attraction can be calculated. Right? All we need is Coulomb's law, which relates the magnitude of the charge and the distance between the ions. All right, we're not going to go into that, but I just thought I'd throw that in for fun. You ever heard of Coulomb? No. I think he was French, but he came up with this rule, and actually it was similar to Newton's law of universal gravitation. The force of the gravitational attraction between 2 heavenly bodies is proportional to their masses, the product of their masses, and inversely proportional to the square of the distance between them. So get them farther apart, the force decreases. Same thing with charges, positive, negative. You pull them farther apart, and the force of attraction decreases. So what that means is, with very small ions that are the same charge as big ions, we'll have a stronger attraction. So if we have lithium and fluorine, compare the force of their bond between the two, compare that to sodium and chlorine. Right? They have the same charges, right? So you should expect similar attraction, but the sodium and the chlorine ions are bigger than the lithium and the fluorine ions. So since the charges are closer together, the strength of attraction will be greater. Right? It's pure electrostatics. Okay, so now let's combine Lewis dot structures so that we can build compounds. All right, so in this case, I don't even have to draw it on the board. We've got sodium. Before the reaction, sodium has this 1 electron in its valence shell. Chlorine has 7 electrons in its valence shell. So sodium transfers that electron over to chlorine, and now chlorine has its octet, and sodium is shown without an octet, but its core electrons still have the octet that looks like neon. But since we transferred that valence electron, now we show nothing around sodium. But we do know that transferring that electron gives sodium a positive charge and chlorine a negative charge, and now they attract one another. And we get that ionic compound of sodium and chlorine. You can do the same thing with oxygen and sodium. Only in this case, oxygen needs how many electrons to make its octet? It needs 2 electrons. Yeah. So it gets 1 from one sodium and 1 from the other sodium. Now we have 2 sodium positives and 1 oxygen with a 2 negative charge. So we've completed the octets and we've got the charges. Notice that the charges balance, right? 2 positives balanced against 1 with a 2 negative charge. And that's going to be the case with all ionic compounds. The charges have to balance. Calcium and chlorine do the same thing. Only this time, the calcium donates 1 electron to one chlorine and 1 electron to the other chlorine. And now calcium has its 2+ charge. Notice calcium is in the second column. It's an alkaline earth. And all of those tend to form a 2+ charge. Whereas chlorine is a halogen with a -1 charge. It takes 2 chlorines to satisfy, to be satisfied, make the octet, and the charges balance. Okay, there's the Lewis structure. The Lewis structure for a compound is a combination of Lewis symbols that represent either the transfer or sharing of electrons in chemical bonds. Now, we haven't talked about sharing yet, but we will. That's coming up. All right, let's just hammer the point home again. All compounds, ionic compounds, are neutral. You have to balance the charges. And all you have to do then is, once you've decided what is the charge on the ion that forms from completing the octet on the ions, how many of each one does it take to balance the charge? Okay, so when we write the formulas for ionic compounds, we always put the cation first. The positive ion comes first. And then we put the negative comes second. And while we may find it convenient to do that, just so that we know the charge is balanced, when you actually write the compound, you leave the charges out. Let me see if I got my... there we go. Just to be sure. Okay. And then you use subscripts in the formula to give the combining ratios of the ions. Remember when we're talking about symbols, right? 4 positions around the symbol. This is going to be the number of atoms. So that's how you adjust the number of atoms when you write the compound. Here's sodium and phosphorus ions. It takes 3 positives of sodium to balance the 3- from the phosphorus. So sodium has a subscript of 3 and phosphorus only has a 1. Remember, we don't write the 1. If there's a symbol there, there's at least 1. You only put numbers below them and to the right if you need more than 1. Okay. How about we do this one? Barium and chlorine. So if we got a barium with a 2+ and chlorine with a 1-, it's going to take 2 of these, right? So 2 times a -1 is -2, and 1 times a 2+ is a +2. So we get 0. This is kind of simple stuff, isn't it? How about this one? This might be interesting. If we have an iron with a 3+ charge and an oxygen with a 2- charge, how are you going to make those balance? I'll get a drink while you're thinking. Use a math trick. Cross multiply. Bring the 2 over here and the 3 over here. So that means a -6, and this is a +6. Okay. Okay. Let's see. How about lead 4+ and oxygen 2-? Right? Those are even numbers. Well, we've got to balance that 4 plus with a 4 minus, right? So we need 2 here, don't we? That'll do it. And we leave out the charges when we write the compound. Correct formula for aluminum 3 plus and chlorine minus 1. We need a subscript of 3 for the chlorine, I think. And that'll balance the charges. Okay, I mentioned this earlier with sodium and chlorine. Solid ionic compounds. And in fact, I can't think of any ionic compounds that are not solids at room temperature. They seem to always be solids. They consist of a matrix of positive and negative ions arranged in such a way that the ion is surrounded by its neighbors of the opposite charge. And that's fairly simple to illustrate with sodium and chlorine because there's positive 1 and negative 1. But what if you have a positive 2 and a negative 1? Well, you have to surround that positive 2 with more negatives. So it changes the structure of the crystal. All right, so that's what you're going to get with calcium chloride crystals. Right, they have a different shape. I think they're shaped like a rhomboid. What's a rhomboid? Well, it's like a 3-dimensional rectangle, right? It's long this way and has square cross section. And then you hold the bottom flat and you take the top and push it sideways. And then you push it forward a little bit. So it's sort of skewed this way and that way. And that's all because of the way that those ions fit together in their crystal structure. Also, I've done this before. You take a crystal of calcite, which is calcium chloride, and you set it on, and it's transparent, and you set it on some print, some type, and you look at it, and it splits it into 2 images. So I'm looking at here, maybe review for exam 2 in green here. It's going to be in 2 places right there. It's weird, but interesting. Okay, so I showed you this one before, sodium and chloride ions. Notice the sodium ions are small because they've lost electrons, whereas the chloride is bigger because it gained an electron. And that's the way they fit together. In the general chemistry class, we're in the 2nd semester now. We just went through our first 2 chapters and actually, discussed the structure of these crystals. You guys won't have to live through that torture, though. This is just illustrative. Okay, that's why, because this the structure of these ionic compounds, it can go on infinitely. They can be really small, they can be big, and the arrangement of the cations and anions is the same all the way through the crystal, no matter how big it is. So what would we say? Like sodium is 3 times 10 to the 35th, and chlorine is 3 times 10 to the 35th. Got that many ions together in a crystal, right? That doesn't make any sense. So what we do is we simplify it to the simplest whole number ratio, right? Divide that by the same number and you get 1 and 1. Right? So when we say this, right, that's the formula unit. Right? It's not a molecule. We're going to talk about molecules in a minute. This is the formula unit for sodium chloride. And the formula unit is used to describe ionic compounds, simply because their structures can go on forever. Right? If you had a single sodium chloride crystal that was like this big, right, it would have the same internal structure as one that was only that big. Okay. So let's just hammering that point home again. formula unit. Okay, so we're gonna, yeah, these are the metals that in ionic compounds have a fixed charge. They always have this charge in an ionic compound. So the first column, the alkali metals have 1+ charge always. The alkaline earths have a 2+ charge. Aluminum, gallium always have a 3+ charge. And these transition metals, zinc and cadmium, have a 2+ charge, and silver has a 1+ charge. Okay. Those metals are always fixed charges. Now that's important to remember when we start naming compounds, so hold that in reserve. Now we're going to get the rules for naming compounds. And believe me, it's very well structured, organized for two purposes. We want to be able to name a compound so that it is unambiguous. Unambiguous, right? And non-redundant. Once we've named the compound, we don't want to have to put information in the name that is already covered by another part of the name. So we want unambiguous names that are not redundant. And we're going to start with what's called a binary compound. That is, there are two elements, right? A metal and a non-metal to begin with. Or it could be a metal, a non-metal, and a non-metal. Right? So up to this point, we've said that when you write the compound, you write the metal first and the non-metal second. For ionic compounds, that's true. But what do you do when you get to non-metal, non-metal? Right? Don't have ions anymore. So we'll have to cover that in just a minute. How do you, which one comes first, right? All right. Type 1 compounds. Type 1s. They're always a metal and a non-metal. Okay, always. But the metal is a fixed charge. The metal always has a fixed charge. All right, so when you combine the two, we'll use sodium and chlorine again. When you combine the two, sodium always has a positive charge. Now, as we didn't mention the nonmetals, but the halogens always have a 1- charge. Right? Fluorine, chlorine, bromine, iodine, they always have a -1 charge in ionic compounds. So if you know that, then we name them by the metal first. We just say the name of the metal. That's it. And then the anion, we change the ending to IDE. So instead of chlorine, we would write chloride. Now, that is unambiguous because we know sodium has a 1+ charge, chlorine has a -1 charge. So we can write this from that name with no mistakes. We just write the sodium, we write the chlorine here. We know sodium always has a +1, chlorine always has a -1. All we have to do now is be sure that the charges are balanced. Okay. What if we do this one? That means we have to have 2 chlorines, and we would name it calcium chloride. That's it. We don't have to say anything about the charge of calcium because it's an alkaline earth It's a fixed charge at 2+ always. If we were to say what the charge was in some form or fashion, that would be redundant, because we already know it's a 2+ charge. We don't need to say what the charge is. Okay, and that's the model for type 1 compounds. Oh, here are the non-metallics, right? Bromine would be bromide. It's a -1 charge. When carbon is combined with a metal, it always has a 4- charge. So we could say, let's see, calcium carbide. That's a good one. Let's name it first. Calcium carbide. So the calcium has a 2+ charge, right? The carbon has a 4- charge. So how do we balance those charges? Well, we need 2 of these, right? And we don't have to say anything about the charge up here. We just say, okay. So now that we have our charge bookkeeping done, we just erase those. It'll be Ca2C. That's calcium carbide. Now, if you've got any grandfathers that used to go in the mines, okay, they probably know all about calcium carbide. Like they put it in their carbide lanterns, right? You just put some of these crystals in your lantern and add water, and it reacts. Water reacts with this and makes acetylene gas. And then you can light it, and you got light underground. Of course, there's a big problem there. That's an open flame. If you get coal dust buildup or methane gas pocket, then that flame is all it needs to get going. So that's why they went to electric lanterns, sealed electric lanterns. But that's calcium carbide. Let's see, the others are fairly straightforward. There's one in there, hydrogen. Whenever hydrogen is combined with a metal, it takes on a -1 charge, because the metal wants to give up an electron, and hydrogen can take it because it's got a 1s1 electronic configuration. It's got room for another electron. So it can either give up an electron or accept an electron, depending on the environment. So if we had, say, magnesium and hydrogen, right, then this is going to be a 2+. This would have to be a -1, so we need 2 of those. So magnesium hydride would be this compound. The rest of them are fairly straightforward. Yeah, there's nothing scary about those. Nothing different. So potassium chloride, right, these are all type 1 compounds. Magnesium bromide, right, just put 2 bromines in here instead of the hydrogen. And calcium oxide. Calcium is in the second column, it's 2+. Oxygen is a chalcogen with a 2-. You only need 1 of each. This is the formula unit, and we balance the charges with just 1 calcium and 1 oxygen. And you can go backwards and forwards. You can write the formula from the name, or you can write the name from the formula if it's of this type, type 1. Okay, all right. Type 2. Type 2s are also metal and non-metal. But the metal, in this case, has a variable charge. Right? It's not one of those that has the fixed charge. First column, second column, aluminum, gallium, or zinc, cadmium, or silver. It's any one of the other metals will have a variable charge. If they're not in the first column, second column, aluminum, gallium, zinc, cadmium, silver. It's any one of those other metals, transition metals, or representative metals that are not aluminum, gallium, like tin or lead, or antimony. Those will have possibility of one or more different charges in that compound. So we need a way to say, what is the charge? We need to identify the charge in the name. All right, we do it with a Roman numeral in parentheses, just behind the name for the metal. Copper, right? Copper is a transition metal. It could have a +1 charge or a +2 charge, right? Depending on the compound. So in this case, we find that the copper and the bromine, like that, means that it's, and we name it similar to this one, but we have to say what the charge is. Oops. Bromide. Okay. Just put the charge right there. Now we know. And if we, let's do lead 4 oxide. If we have the name lead 4 oxide, we know that has oxygen in it, and we know it has lead in it. But until we know the charge on lead, we can't balance the charges. So that's what the 4 tells us. It tells us it's a 4+. We know oxygen is a 2-. So now we can balance the charges with a 2 oxygens. That's how you go backwards and forwards. And you can take this one. If we're given FeS, right? We know sulfur is in the same group as oxygen, so it has a 2- charge. Right? We know from this formula that iron, since there's only one iron, it balances that 2- with a 2+. That's the only way you can do it. Right? You can't give it a different charge. It has to have a 2+ to balance. So now we can write the name. Iron 2 sulfide. Okay. Yes, no, maybe. It takes practice. Practice. Lots of practice in that review document. That'll help you get used to it. Plus the extra credit. You probably want to hold the extra credit until you get comfortable. Besides, we haven't covered all the rules yet. You might guess that there's a type 3 also. Okay. This is a list of polyatomic ions. Let's see, I think, yeah, one of your handouts has all the polyatomic ions in it. It looks exactly like that, only it's bigger print. Notice that the column on the left, all the polyatomic ions are sorted by their names in alphabetical order. So the top one is acetate and the bottom one is thiosulfate. On the right, it's the same polyatomics, but they're sorted differently. They're sorted by the formulas. So either way, you can find them. And the exam, let's see, the review document. Let me find the review document and be sure. My copy of the review document. Here it is. Let's look at the very last page of the review document. See if it's got any name. No, it doesn't. Okay. So any of those handouts I gave you, information like the polyatomic ion list, the one we haven't gone over yet, the solubility list, the one with the gray blocks on it, and the periodic table, those will be in the exam. So you don't have to memorize that stuff. You have a periodic table, you have polyatomic ions, and you have a solubility chart. Okay, I'll be sure it's in there when you get the exam. So if you need the solubility chart and don't have it, then I've got to give you one when you show up. Okay, so these are polyatomic ions. Well, we have to say, all right, what is a polyatomic ion? A polyatomic ion is, worked backwards, it is an ion. That group of atoms has a charge, and the charge on that ion is distributed over the whole ion. So in other words, if you don't have those atoms in a structure together, then you don't have that ion and its charge. Right? They are held together so strongly that they behave as a single unit. Examples: sodium hydroxide. So when you're naming the compounds, you can name them by one of these conventions. If it's sodium, then it's a type 1 because that's a fixed charge. But if it's if it were this one, let's say 3. That hydroxide has a -1 charge spread over the whole ion. And this would have a 3+ charge because you got 3 negatives, has to be balanced by a 3+. So now we know that that iron is a 3+. So it'd be iron 3 hydroxide. Okay. Now, all of those polyatomics, except for one, have negative charges. They're all anions, except for one. And the last one in this list shows you the one positively charged because it's in the metal position. See, it's at first. That's where the cations go. It's ammonium. Ammonium is NH4 with a plus charge. Okay, the rest of them are negatives. Now, notice that some of these have parentheses around them. That's because these polyatomic ions behave as a single unit. You can't change the subscripts. Once you get that structure together, NO3 minus is nitrate. If you need 2 of them, you don't say N2O6. You say NO3 parentheses and then a subscript at the parentheses. And by the way, if you see one like that, then you know, if you see the formula with a parentheses around it, you know that inside that parentheses is a polyatomic ion. And you know to go look for it. If you don't have it memorized, you go to your list and look it up, NO3. Okay. All right. Now for the third one, type 3. The one that we haven't talked about yet, nonmetals and nonmetals. When you get 2 nonmetals together, they cannot form ionic compounds. So you cannot balance a charge. They don't have charges. But we're gonna borrow from the ionic naming convention, the binary convention, and put 2 elements together. And in order to properly identify the formula, we have to say how many of each element is in the unit. And to do that, we need prefixes. So on the next page, yeah, we have prefixes. These are Greek prefixes that each one means a different number, right? Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Okay, so you have to know those. And then we use them. Now, how do we know that it's a type 3? Well, in this case, we've got our example. You got carbon and oxygen in there. Where do they come from in the periodic table? They're both to the right of that heavy line, right? They're both nonmetals. So you know you have to go to the type 3 convention automatically. All right. So in this case, we just say this is in the cation position, but it's not a cation. Don't get me wrong. It's in the cation position. So we name it as if it were carbon. We just say carbon. Then we say how many oxygens? Dioxide. Okay. Now, if there's only one in this position, we'd never say mono in the first one. If you got one in the second position, we do say mono, right? So, for instance, if we had this one, right, that's the one you don't want to breathe. Carbon monoxide. That's the dangerous one. You know how carbon monoxide works? You had anatomy and physiology? Okay. You know how oxygen is carried throughout the body on hemoglobin, on the red blood cells? It's bound to the hemoglobin, the iron in the hemoglobin, right? And then when you get to its destination, the hemoglobin gives up the oxygen, right? Okay. So the bond is just strong enough to hold the oxygen until it gets where it's going. And then your blood picks up carbon dioxide differently. It doesn't bond to the hemoglobin. It's actually in a buffered situation in the plasma itself, mostly. Right? There are a few of them that bond to the hemoglobin, but most of the carbon dioxide is contained in the plasma. Well, if you breathe this stuff, it goes in there and kicks the oxygen off of your hemoglobin. And it sticks there and stays there. So if you're exposed to too much carbon monoxide, you actually suffocate at the molecular level. Right? There's no place for the oxygen to be bound. So it saturates the hemoglobin with carbon monoxide and won't let go. Right? Not fast. By the time it lets go, you're probably dead anyway. Okay, so another example. This one, N2O4. So this will be dinitrogen tetroxide. Notice we dropped the A off of tetra. It just doesn't sound right to say tetraoxide. We say tetroxide. But there are 2 nitrogens and 4 oxygens. So with this name, we can unambiguously write that formula. All right. So what if you are confronted on say a test question with the name of a binary compound? Right? How do you know which rule to use? So you look at the name and say, okay, is it a metal? Is there a metal in here? If there's a metal, you go straight to 1 and 2. Now you need a tiebreaker. Is the metal fixed charge? Right, you know where it comes from. First, second column, aluminum group, or zinc, cadmium, silver. If it's one of those, then you go to type 1 and name it that way. If it's anything else, metal, then you go to this one. And then you deduce from the formula what is the charge on the metal. Once you know the charge on the metal, then you can put the charge in parentheses here, Roman numerals. So that's the procedure. If they're both nonmetals, you go straight to this one and you just say, how many of them are there? And in fact, as far as chemistry goes, this is probably one of the most straightforward processes of any that we will encounter. Some require some intuition, but this one, I mean, it's just mechanical. Bam, 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 bam. Just follow the rules. Now, if you have a polyatomic ion in there, you treat the polyatomic, if it's the ammonium, the 1 positive, it's always going to be here because ammonium is a fixed charge. So you use this convention for ammonium. But if it's a metal and a polyatomic, then you have to decide what kind of metal is it. And the names for the polyatomics are fixed. You don't have to change the endings. You just use that name, right? nitrate, NO3 minus, nitrite, NO2 minus, sulfate, SO4 2 minus. Right, so you just use that name, and you don't have to change the ending like we did here. Now, I can't let you get away before we learn how to name acids. Okay, I'm going to need some room, so I might as well get rid of these. The reason that we have a separate naming convention for acids, when the international control group, IUPAC, International Union of Pure and Applied Chemists, when they got together in the 70s, I think it was, and they had a special committee for naming, and they were setting up new rules for naming. Actually, this Roman numeral convention helped get rid of some confusion, because when I was in my first chemistry classes, we were using the old convention where we said if we had a compound with that one in it, we'd have to say ferrous. If we had this one in it, we would have to say ferric. Instead of iron 2, iron 3. So you guys are lucky. And the problem with that is this us and ick ending, it depends on the element, right? We've got some elements that would be a 2 and a 4 here, like lead. Lead would be plumbus, a 2+, and 4+ would be plumbic. So you guys got off easy. But acids, I think there was a problem because acids came out of the Middle Ages, right? The mineral acids that were used in the Middle Ages by alchemists were already known and named, like hydrochloric acid, sulfuric acid, nitric acid were commonly used during the Middle Ages. So we had to develop some kind of a convention that would take that into account and sort of grandfather in those names and make sense of them. And that's why we have this a separate naming convention for acids. First thing you do when you're going to name an acid. First, you got to say, do I have an acid? Right? And the first thing you look for is hydrogen. If it starts with hydrogen, then you have a candidate for an acid. Now you can have hydrogens anywhere else in the molecule, but these are the acidic hydrogens. So if you have something like this, right? So if you look at your chart, this is the acetate polyatomic ion. And we put a hydrogen out here. This polyatomic ion is a -1 charge. Put the hydrogen out here, it's always a +1 charge when it's the first one in the list. Okay, so this one would be an acid. Even though you've got some extra hydrogens here, those don't count. Just that one counts for the acid. The second requirement is it has to be an aqueous solution. In order for these hydrogens to dissociate and express themselves as an acid, you have to be an aqueous solution. So if we were to say that HCl is our first one, HCl. If you had pure HCl, it would be a gas. And we would name it by our previous convention. So we would say hydrogen, right? It's in the metal position. Hydrogen chloride. Right? In this arrangement, that's always a +1, and this is always -1. So that would be the name of it, hydrogen chloride. If you put it in aqueous solution, though, we need to use an acid naming convention. Okay, so in order to do that, we ask ourselves, is there oxygen in this molecule? No, there's no oxygen in this molecule. That means we start the name with the prefix hydro. If there's no oxygen, you always start it with hydro. And then you look at the other part of the name. This references the hydrogen. Look at the other part, and the "ide" becomes "ic." Right? "Ide" becomes "ic" in this name, and then you follow it with acid. So hydrochloric acid is HCl. Okay. There are other examples. For instance, the one with CN, cyanide, that's a polyatomic ion. So HCN means hydrocyanic. Cyanide becomes cyanic. H2S. Right? Start off with hydro because there's no oxygen. And then sulfide, hydrogen sulfide becomes sulfuric. We say sulfuric. That just sounds better than sulfic. Acid, excuse me. There we go. So these are examples where you don't have any oxygen in the name. When you do have oxygen, it's going to be because there's a polyatomic ion there. I mean, cyanide is a polyatomic, but it has no oxygen. But sulfur's not a polyatomic, chlorine's not a polyatomic. So when you have oxygen, you don't start the name with hydro. So our first example is HNO3. If this were not in aqueous solution, if we named it by our previous convention, we would say hydrogen nitrate. Okay. But if we put it in aqueous solution now, we don't say hydro because there's oxygen. We just take this part of the molecule here, this name, and 8 becomes ic. Oops. Looks like an M. Nitric acid. That's it. 8 becomes ic. If we had HNO2, okay, this would be, this part of the molecule is nitrite. And ites become us's. So we would say nitrous. Nitrous acid. Okay. That's probably on the next slide. H2SO4. Remember we had H2S was hydro sulfuric acid. But H2SO4, since this is sulfate, and we don't say hydro, 8 becomes ic. So we say sulfuric acid. So hydrosulfuric acid is missing the oxygens. The sulfuric acid has the oxygens. And if this is sulfite, if it was SO3, like our example there on the slide, it would be sulfurous. I'm going to talk about the halogen, the oxides of halogen in just a second. Stop me if you have questions. Or I'm moving so fast you don't have time to think. It's possible. All right, so this is a decision tree. Once you've decided you have an acid with that previous hydrogen, 1, 2, 3 hydrogens, whatever, that tells you it could be an acid, and you put it in water. Then you say, does the anion position have an oxygen in it? Then you go to no oxygen means hydro starts. Oxygen means no hydro starts. And you look at the ending of the anion to determine what you call it. Okay, let me check my hard copy to see where we're headed here. Okay. All right. See, is there anything more I want to say about acids before we leave them? No? Just need practice. Which one of these is named incorrectly? KNO3. Right? Type 1, type 2, type 3. That's a metal, right? So it's a 1 or a 2. Then we say, okay, what kind of metal is it? It's an alkali metal, so it only has a +1 charge. Can't possibly have any other. So we just say potassium. And this is a polyatomic, the nitrate ion. Potassium nitrate. That's correct. How about TiO2? Where does titanium come from? Whoa. It's a transition metal. Right? See it right there. Potassium, calcium, scandium, titanium. It could possibly have variable charge. So it's a type 2 compound. So we've got to deduce what is the charge. With this formula, that means oxygen has 2 minus each, which means 4 minus total, right? That means this one must have a 4 plus to balance that charge. So the correct name would be titanium. Oops. Can't spell. Titanium 4 oxide. Right? Oop, that's wrong. They got titanium 2. How about the others? Well, let's see. SnO4, SN with a hydroxyl taken 4 times. Each one of these has a minus. So that means this one has a 4 plus. Right. So 10,4 hydroxide, that's right. How about this one? Phosphorus and bromine in this ratio. Right? We know that's what type? Type 3, non-metal, non-metal. So we say phosphorus, pentabromide. That's right. How about CaCrO4? If you're wondering, you don't have parentheses in the compound to identify polyatomics. There's only one of them. If you've got 3 elements or more, and one of them is an oxygen, then you probably have a polyatomic there. So you ought to check it out. In this case, we do. Chromate is a polyatomic, CrO4, right? And it has a 2 minus charge. It's in your list. Look it up. That means we only need one of each. Plus, calcium is an alkaline earth. It has a fixed charge of 2 plus. So calcium chromate is correct. You just need one of each. Okay. We're going to be getting down to the wire here. We've been at it, including the exam, since 9. That's over 2.5 hours. Probably getting kind of tired by now, aren't you? We're getting close to the end. So, I think these slides are out of order. This polyatomic discussion should have come, maybe the list should have come later and we talk about polyatomics now rather than when we did. But the cow's out of the barn, so we go with it. The polyatomic ions, though, this is one of those cases where we have a combination of ionic bonding and covalent bonding. The covalent bonding is inside the polyatomic. That's what holds the polyatomic together as a single unit. You know what? We left off some important discussion. Oh no, covalent bonding is next week. Okay, so we're finishing off with naming compounds, and we're going to talk about the covalent bonding next time we meet. Okay, so I'm not going to steal my thunder today. So that's why the polyatomics, when they're in a compound, if you need more than one polyatomic ion, you can't change the subscripts because that unit is tightly bound and will not accept changes to its ratio. In order to get more of that charge, you need parentheses. Most polyatomic ions have negative charge except for ammonium. We didn't talk about hydronium. We'll get to that. Let's see. When we talk about acids, bases, and salts at the end, we'll introduce that hydronium ion, but you don't have to deal with it right now. Most of the ions contain oxygen except for cyanide and ammonium. And two of the negatively charged polyatomic ions, OH minus and CN minus, have names ending in come on. That was the little Jenny yelling for us to run. Hydroxide ends in IDE, cyanide ends in IDE, and the rest of them have endings like ATE or ITE, and some of them have prefixes. Oh, so let me give you this one. There are some patterns in those polyatomic ions, and this is probably the most extensive pattern is the one that combines chlorine and oxygen. So if we have 3 oxygens, that one is chlorate. And if we take away an oxygen, still has a negative charge, this is chlorite. Now we don't have any more suffixes that we can add to it, so we have to go to a prefix. So we take away another oxygen, this is hypochlorite. Right? Like hypodermic needle underneath the skin, this is underneath the chloride. Or we can add one more oxygen here, and this is perchlorate. Right? So there's a family, a progression with different oxygens in them. And if you learn that progression, then you can master these 4. Plus, chlorine is a halogen. If you go down to bromine, you can substitute bromine in there too for each one of these. And then the name becomes bromate, bromite, hypobromite, or perbromite. Or you can substitute iodine in there, all the way down. So this would be periodate, iodate, iodite, hypoiodite. So with that methodology, you can master 12 polyatomic ions, just like that. The others have similar trends, some of them, but they're not as extensive as this one, like sulfate and sulfite. That's as far as they go. But you can add hydrogen on the front of them. If you add hydrogen on the front of this one, that plus takes away one of these charges. So now it's like that. In this case, that polyatomic is hydrogen sulfate. Yeah, hydrogen sulfate. So I just wanted to show you that. Hydronium, ammonium, they end in IUM. That number 4 references this arrangement. So you can go from sulfate to hydrogen sulfate and the charge changes in this case. Those cases, the charge stays the same, but here it changes because that hydrogen is assumed to be a positive charge, which neutralizes one of the negatives. And you can do that with phosphate also. So there's your polyatomics. Yeah, polyatomics cannot be modified, but they can be used as single charge units when you're balancing your charges. Let's see. Potassium nitrate, is that one right? Wait a minute, we already did this one, didn't we? Oh, all right, we found the incorrect one in the first time we tried it is that one. But how about SN, which is 10? 10,4-hydroxide? Yep, that's right. How about ammonium sulfite? Yeah, you need 2 ammoniums because there's only 1+ charge each. And sulfite is a 2- charge. And then calcium chromate, we did that one already. I wonder how that slipped in there. Correct chemical formula for ammonium carbonate. You ever drink pop? Carbonated beverage. That carbonate is what is in solution. Let's do this and then I'll talk about that some more. So ammonium is like that, and carbonate is like that. So we need 2 of them to balance the charges. Okay, carbonate. So a carbonated beverage is actually you dissolve carbon dioxide gas in water, right? And what happens is you transfer an oxygen over to that group, and it carries with it 2 negative charges. So you have this carbonate, right? Now what do you have left over? Well, you got an oxygen and a hydrogen left over. Is that right? No, we took the negatives with us. Let's see. Actually, you get this. So there's a carbon here, a carbon there, 2 oxygens and 1 oxygen, 3 oxygens, and then the other carbon. So you get that. This is very unstable in aqueous solution. What it wants to do is it wants to go back to that. So when you crack the top on your pop bottle, it goes, it's releasing carbon dioxide from this chemical. Okay. Let's see what we got here. Concept question. That means we're almost at the end. After placing a soft, lustrous, and malleable material in a container of yellowish gas, a violent reaction occurs, leaving a white crystalline material. You decide to break the rule, never taste chemicals in the laboratory, and find that it tastes very salty. Which of the following is correct? Okay, so if it's a soft, lustrous, malleable material, that's a metal, some kind of metal. So a metal is reacting with a yellowish gas, which is probably a non-metal, because there are no gases on the metallic side of your chart. There's only one liquid, mercury. So it has to be a non-metal. You got a metal and a non-metal together. We know that. So this is a solid and this is a gas. And it yields a salty taste. Okay. That looks like nitrogen. Let me do this. Non. There we go. Non-metal. Okay. Not enough information is provided to determine what the two materials and products are. Well, yeah, we're given clues, but we really can't tell what they are. The two materials are likely to be the elements sodium and chlorine, reacting to share electrons to produce a molecular compound, sodium chloride. That could be. We know that chlorine is a yellowish gas, right? And we know that sodium, being a metal, is soft and lustrous, and the reaction between the two will be very violent. The further apart metal and non-metal are on the periodic table, the more violent the reaction. So maybe B. The two materials are likely to be elements sodium and chlorine, both reacting by a transfer of electrons to produce an ionic compound. Isn't that what the B said? Oh, no, the key there is share. Notice it says share electrons. No. If it's sodium and chlorine, they're going to transfer electrons. So maybe C. The two materials are homogeneous compounds reacting. No. So we might take a guess at C, but to be definitive, A would be a better answer. Right? Okay, so the authors are claiming that we've got enough information to say C. I would tend to disagree. But who am I? I just deliver the bad news. Okay. We're going to fill in the table. Notice this table has 1, 2, 3, 4 in those boxes. That means for the first one, we want to put a name for that compound. And for number 2, we want a name for that compound. For number 3, we want the formula for that compound. Number 4, we want the formula for that compound. Okay, so let's do them. This one, NaHCO3. All right, type 1, type 2, type 3. It's got to be a 1 or a 2 because there's a metal. And sodium is a fixed charge, so it's type 1. So we're going to say sodium. And then what is this? HCO3. We have to look it up, right? That's hydrogen carbonate with a -1 charge and +1 charge. So that's the name. All right. Yeah, let's do 2. Mg HCO3 taken twice. Well, this would just be magnesium. Right? Magnesium is a fixed charge. Magnesium, hydrogen carbonate. Okay, so that's number 2. Number 3, sodium phosphate. Sodium phosphate. Okay. We're going to use the type 1 convention because sodium is fixed charge. So we're at the sodium. And then the phosphate, we have to look it up. Right? It's PO4 with a 3- charge. So we need 3 of those without the charges, of course. Okay. And the last one, magnesium phosphate. Okay. Magnesium is a fixed charge. So we say magnesium with a 2+, and phosphate with a 3-. So there we have an odd and even again. So what's the rule? Cross multiply, yeah. So we put a 3 over here and a 2 over there. Now let's see which one matches. Let's see. This is 1, this is 2, this is 3, and this is 4. So 1 is sodium hydrogen carbonate. So it's either B, C, or D. We can eliminate A. All right, so the second one is magnesium hydrogen carbonate. Oh, they're saying bicarbonate. Okay. Bicarbonate is a trivial name. It's not officially accepted by IUPAC now, but hydrogen carbonate is also called bicarbonate. That's an old way of saying the bi refers to hydrogen, bicarbonate. So B, C, or D could be it. Let's look at 3. Na3PO4, Na3PO4. B, that's the only one it could be, right? So is this one right for B? Yep. Okay, so it should be B. I think that's it, isn't it? Yep. That's the last one. Okay. So next week, we're going to get into chapter 5. And we're going to have a lab, determining density. So read up on the lab so you won't be lost. And you can start working on that extra credit now if you want. Oh, hold on a second. There's one rule in there. I mean, it's in the first page of that extra credit. It talks about this. Let me describe it for you. It's another naming convention that's not in the slide set. Some compounds have ionic compounds. Also, when they crystallize, they trap water in their structure. So these are water molecules that are trapped in the structure of the compound. And to get them out, you can't just heat it to 105 degrees Celsius, like boiling point of water, and get them out. You got to heat it higher because you got to drive them out of the crystal. Those are called waters of hydration. And when we name the compound, we just name the ionic compound, and then we tack the water on the end. Okay, so for instance, if we have this compound, zinc sulfate, is that right? Yeah, zinc is a 2+, sulfate's a 2-. Zinc sulfate, it's a type 1 compound. But very often it will have 5 water molecules. No, excuse me. This is 7. 7 water molecules as part of the structure. So for each one of these, you have 7 of those together with it. And we write that like that. We put a dot right here in the middle of the, not down to the bottom, not top, right in the middle. Okay, that's zinc sulfate. Let's see, zinc. Yeah, that's right. Just checking myself. Zinc sulfate, and then we say how many waters, and we use those Greek prefixes. We say heptahydrate. And hydrate stands for water. Actually, it's an ancient construction. Hydra means hydrogen, and ATE stands for oxygen. So it's hydrogen, oxygen, water. So whenever you see this, you know that you write this one like you would any other compound that we've named by convention, and then you tack on the heptahydrate this way. Okay, you don't use a parentheses and a suffix, you use a prefix. And we'll get prefixes again when we balance equations. They're called coefficients. All right, so with that information, you should be able to complete that extra credit. And the extra credit's not due until the next exam. So you've got plenty of time to do it. And if you forget some of the rules, the first page of that extra credit has some rules in this box up here. Unless if you start reading them and they confuse you, then don't look at them anymore. Just go back to the video and that should straighten things out. So let me stop the share.